Before we travel to the quiet regions of the cosmos where gravity grows faint, let us begin with a softer thought experiment, one that unfolds not with violence, but with wonder. Imagine, just for a moment, that the pull of Earth's gravity simply fades away. There is no sound to announce it, no flash, no tremor, no warning. One instant, gravity is the constant companion it has always been, the gentle but unyielding force holding oceans to their basins, air to the planet, and your body to the ground beneath you. The next instant, that invisible embrace is gone. At first, you might not even notice. Your body, your chair, the walls around you, everything shares the same motion, the same sudden freedom. But within a heartbeat, the familiar pressure of weight vanishes. The subtle compression in your spine eases. The soles of your feet no longer press into the floor. Objects that were resting begin to drift, slowly, almost shyly, as though unsure they are allowed to move. A glass on a table does not shatter. It simply lifts, turning lazily in the air. Dust rises in delicate clouds, sparkling in the light. A curtain no longer hangs, it extends outward, as if reaching into an unseen current. Every loose object, every drop of water, every person begins to float, suspended in the same gentle release. Outside, the transformation is even more profound. The atmosphere, no longer bound tightly to the planet, starts to expand, not in a sudden explosive rush, but in a vast, slow exhalation. The air closest to the surface drifts upward, molecules wandering into higher and higher altitudes, following straight paths into space. The sky would begin to darken, not because night has fallen, but because the blanket of air that scatters sunlight is thinning, stretching away into the void. The oceans respond with a similar grace. Water, freed from the weight that once shaped it into seas and waves, begins to rise in enormous, silent swells. Whole sections of ocean lift from their basins, breaking apart into colossal floating globes and winding streams. Sunlight refracts through these drifting masses, turning the space above Earth into a slow ballet of liquid spheres, each reflecting continents and clouds in warped, shimmering patterns. On the surface, mountains and cities remain intact for a time, not because they are still held down, but because they are already at rest. Without gravity, there is no force pulling them away from the planet either. The Earth itself, however, is no longer a tightly bound sphere. Its shape has always been the result of gravity pulling every bit of rock and metal toward the center. Without that pull, the deep interior begins to relax. Over hours and days, the planet would slowly deform, bulging in places, cracking in others, its molten core shifting without the pressure that once confined it. You, meanwhile, are drifting. Your sense of up and down has vanished, replaced by a quiet disorientation. Every motion sends you gliding in the opposite direction, your body obeying Newton's first law with perfect indifference. A gentle push from a wall sends you sailing across a room. Breathing feels different too. Air no longer settles. Exhaled carbon dioxide forms a faint cloud around your face unless you move, unless you create currents with your hands or the motion of your body. As the hours pass, the changes grow larger in scale. The moon, once held in orbit by Earth's gravity, is no longer bound to us. It continues along the path it was following at that instant, moving in a straight line through space, slowly drifting away from the place where Earth used to hold it captive. Tides cease to exist. The delicate gravitational dance between Earth, Moon, and Sun dissolves into independent motions, each body following its own trajectory through the solar system. Earth itself is no longer in orbit around the Sun. Our planet had been falling endlessly toward the Sun, always missing because of its sideways motion. Remove gravity, and that endless fall ends. Earth continues forward along the direction it was moving at that moment, leaving behind the curved path that once defined a year. The seasons stop. The familiar cycle of constellations freezes, then gradually shifts as our viewpoint through the galaxy changes in a new, linear way. Yet even in this grand unraveling, there is a strange calm. There are no roaring winds, no crashing impacts driven by weight. Everything moves according to inertia, according to the simple rule that motion continues unless something interferes. The violence we associate with falling, with collapse, with impact, is absent because those are all children of gravity. In its absence, the universe feels almost eerily polite. Over longer timescales, the consequences deepen. Without gravity to compress its interior, Earth can no longer sustain the pressures that keep its core hot and active. The geodynamo that generates our magnetic field weakens and fades. Without a magnetic shield and without a bound atmosphere, the surface becomes exposed to the raw environment of space. Radiation from the sun and distant stars streams in unfiltered. Temperatures swing wildly between scorching sunlight and deep cosmic cold. The drifting atmosphere thins until breathing becomes impossible. Water, once gathered in oceans and clouds, disperses into vapor and ice crystals, forming vast, tenuous halos around the disintegrating planet. Life, adapted over billions of years to a world shaped by gravity, finds itself in an environment it was never designed to endure. And yet, step back far enough, and even this transformation becomes just another pattern in the universe. A once-living world, unbound, gradually dispersing into a stream of rock, gas, and dust, joining the countless other fragments that wander between the stars. The atoms that once formed mountains, oceans, and living cells continue on, following straight paths through the curved geometry of space-time, shaped by other masses far away. This thought experiment reveals something subtle but profound. Gravity is not merely the force that makes things fall. It is the quiet organizer of structure. It is the reason planets are round, why atmospheres cling, why oceans have shores, why stars ignite, and why galaxies hold together as grand, rotating systems instead of dissolving into diffuse fogs of matter. When gravity vanishes, structure loosens. Boundaries blur. The distinction between surface and sky, between ocean and space, between planet and orbit begins to fade. What remains is motion, pure and simple, guided only by the paths objects were already following. Now, let your mind soften the scenario. Let go of the long-term loss, the planetary changes, the dispersal into space. Return instead to that first, quiet moment, the instant after gravity releases its hold. You are floating, not falling. The world around you is drifting in slow motion. There is no pressure on your body, no weight in your limbs. Every movement is gentle, every interaction unhurried. In that moment, you are experiencing something astronauts know well, and something the universe provides naturally in certain rare and remarkable places. True weightlessness, not because gravity everywhere has vanished, but because its effects have been balanced, minimized, or rendered almost imperceptible. The complete disappearance of gravity from Earth is only a thought experiment, a doorway for the imagination. In reality, gravity never truly switches off. It weakens with distance. It competes with other gravitational pulls. It can be balanced by motion, as in orbit, or by precise alignments of massive bodies. The universe, vast beyond easy comprehension, contains regions where the pull from all directions nearly cancels out, where space-time lies almost flat, and where an object could drift for ages without feeling a significant tug from any nearby mass. These are the places where our gentle thought experiment becomes, in a different form, real. Not on the surface of a planet, but in the deep architecture of the cosmos. Not through the sudden loss of a fundamental force, but through the exquisite balance of many. So keep that feeling with you, the quiet suspension, the absence of weight, the sense of drifting without urgency or fear. Let it shift from an impossible earthly event into a cosmic journey, one that carries us away from our familiar world and into the vast, delicate regions where gravity's influence grows faint, and the universe reveals just how softly it can hold itself together. Close your eyes for a moment and imagine the feeling of floating, not the sudden drop of falling, but the calm and gentle suspension of true weightlessness. In your mind, release the invisible connection that keeps you anchored to the earth. Notice the absence of pull, the soft stillness of drifting without effort. This is not only a dreamlike idea, it is a real condition that exists in certain extraordinary regions of our universe, places where gravity, one of the most fundamental forces of nature, loosens its hold and allows matter to simply exist, unbound and free. Gravity is often described as the weakest of the fundamental forces, yet it quietly shapes everything we know. It bends the very fabric of space and time, gathering vast clouds of hydrogen into shining stars, guiding planets along their steady orbits, and holding entire galaxies together across distances that are almost impossible to imagine. We are so used to its constant presence that we rarely pause to notice it, this invisible structure that gives weight and form to our daily lives. Yet the universe is unimaginably vast, and within it are regions where gravity becomes incredibly faint, where the fabric of space-time lies nearly flat and undisturbed. These places are not always simple empty voids, even though some of them are among the emptiest regions that exist. They are locations where the influence of gravity becomes extremely small, where different gravitational pulls balance each other so precisely that objects can remain in delicate equilibrium, or where sheer distance from stars and galaxies makes their pull almost impossible to feel. Some of these regions have been identified through careful observation and precise calculation. Others remain theoretical, living for now in the elegant language of physics, waiting to be confirmed, or perhaps always remaining ideas that guide our understanding. To understand where gravity nearly disappears, we first need a gentle understanding of what gravity truly is. In the time of Isaac Newton, gravity was described as a force acting across distance, drawing objects toward one another. The strength of this pull depended on how massive the objects were and how far apart they stood. This description worked beautifully for centuries and helped humanity travel to the moon and explore the solar system. Later, Albert Einstein revealed a deeper perspective. Gravity, he showed, is not simply a force in the usual sense. It is the curvature of space-time itself, shaped by the presence of mass and energy. Objects move along the natural curves of this geometry, following the smoothest possible paths, and we experience this motion as gravitational attraction. So when we speak about places where gravity is barely present, we are really describing regions where space-time is only very gently curved, where the geometry of the universe is close to flat. These are areas far from large concentrations of mass, where the subtle bending caused by stars and galaxies becomes almost undetectable, or special locations where multiple gravitational influences cancel each other with remarkable precision, creating quiet pockets of balance within a universe defined by motion and pull. The journey we are about to take is a peaceful one. Together, we will drift through some of these remarkable regions. We will visit points in space where opposing gravitational influences balance so well that an object could linger there with almost no sense of weight. We will move into immense cosmic voids, the largest known structures in the universe, where hundreds of millions of light years separate us from significant clusters of matter. We will imagine the deep spaces between galaxies, where solitary stars wander in near isolation, feeling only the faintest whisper of distant gravity. We will also explore ideas that remain theoretical, places suggested by the laws of physics where gravity might behave in subtle and unexpected ways. And we will gently look ahead to the far future, a time when the expansion of the universe may carry everything so far apart that gravity becomes almost irrelevant across most of cosmic space. This is not a journey filled with danger or urgency. There are no explosions here, no sudden disasters, no dramatic warnings. Instead, this is a meditation on some of the quietest environments that exist, places where one of nature's most important forces grows soft and subtle. Each location offers its own sense of calm, its own invitation to reflect on the vastness of the cosmos and the delicate balance of forces that shapes everything we see. As we move through these ideas, allow yourself to relax into them. Let the concepts flow gently through your mind, like slow and steady waves. There is no need to hold on to every detail or remember every scientific term. Simply let your thoughts wander across these cosmic landscapes, these regions of near weightlessness scattered throughout the universe. Let the ideas become soothing, almost like a lullaby, guiding you through the quiet structure of space-time itself. The universe is not the same everywhere when it comes to gravity. It has regions of strong curvature and regions of gentle calm, places where space-time bends deeply and others where it remains almost flat. We are going to explore the gentlest regions, the broad and quiet expanses where gravity's influence is light and subtle. These are among the most peaceful locations imaginable, even though they lie far beyond our physical reach. Still, through science and imagination working together, we can travel there in our minds, understand their nature, and feel a sense of wonder at their existence. So make yourself comfortable, settle into stillness, and prepare to drift through the quiet regions of the universe, the places where gravity becomes a whisper and where the cosmos itself seems to pause, resting in a deep and gentle calm. In the graceful gravitational relationship between two massive bodies, there are 5 special locations where the pulls of gravity and the motion of orbit come into a delicate balance. These are known as Lagrange points, named after the mathematician Joseph Louis Lagrange, who described them in the 18th century while studying the complex motion of 3 bodies in space. At these points, a smaller object can share the motion of 2 larger ones, remaining in a steady position relative to them with very little effort, almost as if it is gently hovering in space. Picture the Earth and the Sun moving together in their long and ancient orbital rhythm. The Sun, with its immense mass, shapes the gravitational structure of the inner solar system, while Earth, though far smaller, still creates its own region of influence. Where these influences combine in just the right way, and where orbital motion adds its steady outward tendency, there appear zones of balance. These are not places where gravity disappears, but regions where different pulls work together so precisely that the result feels calm and nearly weightless within that shared motion. The first of these locations, called L1, lies between Earth and the Sun along the line that connects them. In the Earth-Sun system, this point sits about 1.5 million kilometers from Earth in the direction of the Sun. Here, the Sun pulls strongly on any object, but Earth's gravity slightly offsets that pull. Together, and combined with the motion of orbit, they create just the right conditions for an object to circle the Sun in step with Earth, even though it is a little closer to the Sun. The balance is gentle but not perfectly stable, so spacecraft place their need small adjustments from time to time. Even so, L1 acts like a quiet pocket in space where the competing influences of 2 worlds meet in near equilibrium. A well-known spacecraft called the Solar and Heliospheric Observatory has spent many years near this L1 point. From there, it watches the sun continuously, never slipping behind Earth's shadow. In this location, the spacecraft is guided by both the sun and Earth, yet the combined effect allows it to remain almost fixed relative to our planet as both continue their shared journey around the sun. It is a beautiful example of gravitational balance in action, a place where motion and attraction blend into a steady and useful stillness. The second point, L2, lies on the far side of Earth, away from the sun, but still along the same connecting line. This point is also about 1.5 million kilometers from Earth. At L2, the sun's pull and Earth's pull act together in a way that allows an object to orbit the sun with the same period as Earth while staying just beyond our planet. Like L1, this point is not perfectly stable, and small corrections are needed to remain nearby. Even so, it offers a calm and practical environment, especially for space telescopes that need a dark and quiet view of the universe while still staying within reach of communication with Earth. The James Webb Space Telescope operates near this L2 region. From there, it looks deep into space and far back in time, studying distant galaxies, newborn stars, and the faint glow left over from the early universe. In this location, the gravitational environment is gentle in the shared Earth-Sun frame of motion. The Sun and Earth remain in roughly the same direction, and large protective shields keep the telescope cool and shaded. With only occasional small adjustments, the observatory can remain in this balanced region, floating in a place where gravity is carefully countered by motion, creating a stable platform for quiet exploration. The third Lagrange point, L3, lies on the opposite side of the Sun from Earth, at about the same distance from the Sun as our planet. This location has inspired many imaginative stories about hidden worlds forever concealed behind the Sun. In reality, careful observations show that no large object waits there, and this point, like L1 and L2, is not truly stable over long times. Still, it remains a special solution in the mathematics of motion, another place where gravity and orbital movement come into a precise but delicate balance. The fourth and fifth points, known as L4 and L5, are especially interesting because they can be stable under the right conditions. These points lie along the orbit of a planet, 60 degrees ahead of it and 60 degrees behind it, forming an equilateral triangle with the planet and the Sun. At these locations, an object can remain for very long periods, moving in gentle loops around the point rather than drifting away. This stability has allowed large groups of asteroids to gather in Jupiter's L4 and L5 regions. These are called Trojan asteroids, and thousands of them share Jupiter's orbit around the Sun, always leading or following the giant planet at a steady angle, never colliding with it. At L4 and L5, gravity is still very much present, but the overall pattern of forces creates natural gathering zones. The Sun provides the main pull, while the planet adds a secondary influence. In these special positions, the combined gravitational effects and the motion of orbit work together in a way that keeps objects confined to a stable region. They circle the Sun in harmony with the planet, maintaining their triangular arrangement as the entire pattern moves through space. Lagrange points are not unique to Earth and the Sun. Every pair of orbiting bodies has its own set of 5 such locations. The Earth and the Moon have Lagrange points as well, with some of them lying relatively close to the Moon. These regions may one day be used for communication relays or staging areas for missions traveling deeper into space. Other planets and their moons also have similar points, and even pairs of stars orbiting each other create their own gravitational balance points. Across the galaxy, wherever 2 massive objects move together, These quiet regions of equilibrium naturally arise from the laws of physics. In all these cases, Lagrange points show us that gravity does more than simply pull objects together. When combined with motion, it can also create balance. These are places where the complex landscape of gravitational influence forms gentle valleys and stable plateaus, areas where an object can remain with minimal effort, sharing in the motion of larger bodies without being drawn strongly toward either one. What makes these points especially fascinating is that they appear everywhere the same basic conditions exist. The mathematics that describes them is universal. Around distant stars, in binary systems, and in planetary systems far beyond our own, similar points of balance quietly exist. Most of them may remain empty, unnoticed locations in space where the balance is present but unused. Others may collect dust, rocks, or even larger bodies, holding them in place for millions or billions of years. As we leave these Lagrange points behind in our journey, we carry a deeper sense of how gravity can create not only attraction but also stillness. These regions are not voids where gravity has vanished, but carefully balanced environments where different influences meet in harmony. They are gentle harbors in the vast gravitational ocean, places where objects can linger, suspended in a quiet and elegant balance, barely aware of the powerful forces that surround them. If you could step far beyond our galaxy and look at the universe on its largest scales, you would see a pattern that is both surprising and beautiful. Galaxies are not scattered randomly through space. Instead, they gather along enormous filaments and walls, forming a vast cosmic web that stretches across the observable universe. Between these glowing threads lies immense darkness, huge regions containing very little matter, extending across hundreds of millions of light years. These are cosmic voids, the largest known structures in existence, enormous bubbles of near emptiness where gravity is incredibly faint simply because almost nothing is there to create a noticeable pull. One of the first major voids discovered was identified in 1981 by astronomer Robert Kirshner and his team. While mapping the positions of galaxies, they noticed a region in the constellation Boötes where galaxies were strangely scarce. This area, now called the Boötes Void, spans about 330 million light-years in diameter. Within this vast volume, far fewer galaxies exist than we would expect based on the average density of the universe. It is not completely empty. Around 60 galaxies have been found inside it, but compared to typical regions of space, it is extraordinarily sparse. To sense the scale, consider that our Milky Way galaxy is about 100,000 light-years across. The distance to the Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years. The Boötes Void is more than 100 times larger than that distance, a region so immense that light itself takes 330 million years to travel from one side to the other. Within such an expanse, gravity as a strong, shaping force barely makes itself known because there is so little mass present to curve space-time. Voids are not rare accidents. They are a natural and essential part of the universe's large-scale structure. Modern cosmology shows that matter in the universe is arranged somewhat like a sponge or foam, with galaxies concentrated along the surfaces of enormous bubble-like regions. Inside the voids, there is very little dark matter and very little ordinary matter, only thin traces of gas and the occasional isolated galaxy. Some voids may be even larger than the Boötes Void. One possible supervoid linked to a feature in the cosmic microwave background, sometimes called the cold spot, may stretch close to 2 billion light-years across, though scientists are still studying and debating its true nature. The origin of these vast empty regions goes back to the early universe. Shortly after the Big Bang, matter was spread almost evenly, with only tiny differences in density from place to place. These small variations became the seeds of all future structure. Regions that were slightly denser had a bit more gravity, which drew in additional matter and made them denser over time. Over billions of years, this process built galaxies, groups, and clusters. In areas that began slightly less dense than average, the opposite happened. With weaker gravity, matter gradually flowed away toward denser regions. As time passed, these underdense zones lost more and more material, becoming emptier while surrounding structures grew richer. The voids expanded as matter drained outward, helping to shape the web of filaments and walls that we observe today. In this sense, voids are not just gaps that never filled in. They are regions actively carved out by gravity, places from which matter has slowly migrated elsewhere. If you were somehow inside a large cosmic void, the gravitational environment would feel unlike almost anywhere else. The nearest galaxies might be tens or even hundreds of millions of light years away, so distant that their gravitational influence would be practically undetectable. There would be no nearby stars, no planets, no bright points of light close at hand. The curvature of space-time in such a place would be extremely small, very close to flat. An object placed in the middle of a void would experience almost no gravitational pull in any one direction. It would drift in near perfect balance, with only the faint combined tug of extremely distant structures gently canceling out across vast distances. Voids are not perfectly empty. They contain traces of gas, mostly hydrogen and helium left over from the early universe, but at incredibly low densities. Even the best vacuum chambers on Earth still contain countless particles in each small volume. In contrast, parts of intergalactic space within voids may contain only a few atoms in a space the size of a room, sometimes even less. It is a level of emptiness far beyond anything we can create in a laboratory, a near-perfect natural vacuum. From deep within a void, the sky would look very different from ours. Instead of a bright band of the Milky Way stretching across the night, you would see a mostly dark sky with only a few extremely faint smudges of light marking the positions of very distant galaxies. There would be no sense of being embedded in a grand spiral of stars, no nearby companions in space, only profound isolation in every direction. And yet, there would also be a deep calm in such a place, a region where the usual gravitational bustle of the cosmos falls nearly silent and space-time rests in broad, gentle stillness. These voids are also affected by the expansion of the universe. Space itself is stretching due to a mysterious component known as dark energy, which makes up most of the universe's total energy content. This expansion becomes more noticeable on the largest scales, and voids, with so little matter inside them, offer little resistance. As a result, they tend to grow over time, becoming larger and emptier as galaxies are carried farther apart. Billions of years from now, these regions will be even more vast and even more quiet than they are today. Cosmic voids are important for understanding the universe as a whole. Their sizes, shapes, and distribution match the predictions of our leading cosmological model, which includes dark matter and dark energy. By studying voids, scientists can test how gravity behaves across enormous distances and look for subtle clues about the nature of dark energy. Some researchers have even suggested that very large voids might influence the light from the early universe, slightly altering the temperature patterns we see in the cosmic microwave background. These ideas are still being explored, but they show how even the emptiest regions can help us learn about the deepest laws of nature. There is something quietly moving about the idea of cosmic voids, these immense sanctuaries of emptiness where gravity becomes little more than a whisper. They remind us that the universe is shaped not only by what is present, but also by what is absent. In our daily lives, we are surrounded by matter and constantly aware of gravity's pull. But on the grandest scales, much of the cosmos consists of these huge open spaces where almost nothing interrupts the smooth geometry of space-time. When we reflect on cosmic voids, we are really reflecting on space itself, the vast stage on which galaxies, stars, and planets appear as brief patterns. In the voids, the stage is nearly bare. There are few actors, little movement, and an extraordinary sense of stillness. These are among the quietest places in the universe, regions where gravity barely exists not because it has been canceled by other forces, but because there is simply too little matter to bend space-time in any significant way. When we picture galaxies, we often imagine bright islands of stars drifting in a sea of perfect emptiness. Yet the universe is more subtle and more serene than that. Between galaxies, especially those gathered together in clusters and superclusters, there is a faint, almost ghost-like presence of gas, plasma, and the occasional wandering star, all spread across distances so vast that the mind can only soften into the scale. This region is known as the intergalactic medium, and it is a realm where gravity still exists, yet only as a whisper, where the pull of distant galaxies is so gentle that space-time itself is only slightly curved, almost smooth and calm. Within galaxy clusters, where hundreds or even thousands of galaxies share a common gravitational home across millions of light years, the space between them is filled with extremely hot plasma. This material has been heated by gravitational compression and by energy released from active galactic centers, and it glows softly in X-rays. Even here, the density is unimaginably low compared to anything on Earth, perhaps a single particle in a cubic centimeter, but on cosmic scales this is considered relatively dense. Move beyond these crowded regions, into the wider stretches between isolated galaxies or even between clusters, and the intergalactic medium becomes thinner still. Astronomers call much of this the warm to hot intergalactic medium, with temperatures ranging from hundreds of thousands to millions of degrees, yet with densities many times lower than even the thin plasma inside clusters. In these quiet expanses, there may be only one particle in many cubic centimeters of space. Gravity here is present, but so weak that its influence fades into the background, and space-time curvature becomes almost imperceptible, like a calm ocean without waves. Imagine drifting in such a place, perhaps halfway between the Milky Way and the Andromeda Galaxy, about 1.25 million light-years from each. Their gravity would still reach you, but only faintly. The acceleration would be a tiny fraction of what we feel standing on Earth, so small that for any human timescale, or even for millions of years, you would seem to float in near stillness, not truly orbiting either galaxy, just resting in the vast balance between them. Over billions of years, you might slowly drift one way or the other, but in the short span of civilizations, nothing would seem to change. We know that objects really do inhabit these remote regions. Astronomers have discovered rogue stars that no longer belong to any galaxy, likely thrown out by powerful gravitational encounters or by the chaotic dance of merging galaxies. Once ejected, these stars travel alone through intergalactic space, guided only by their original motion and the faint combined pull of faraway structures. They shine in isolation, separated from the dense stellar cities where they were born. There may also be rogue planets, worlds that were cast out from their parent systems or that formed on their own from lonely clouds of gas. Studies suggest that even within our own galaxy there could be billions of such wandering planets, so it is natural to imagine countless more adrift between galaxies. On a distant rogue world, if internal heat were somehow preserved beneath a frozen surface, there might be hidden oceans and perhaps even life, existing in total darkness. unaware of the galaxies scattered thinly across the sky, feeling almost no gravity beyond that of its own small globe. The intergalactic medium is not frozen in time. It slowly changes as galaxies live and die. When massive stars explode as supernovae, they scatter newly forged elements into space. Some of this material escapes the galaxy entirely, enriching the intergalactic medium with traces of carbon, oxygen, iron, and other elements that were once locked inside stars. So even this near-empty realm carries the quiet memory of stellar life, the ashes of ancient suns dispersed across millions of light years. In the deepest cosmic voids, far from clusters and filaments, matter becomes even more rare. Here we approach the lowest densities found anywhere in the universe, where gravity is shaped not by nearby objects, but by the broad, gentle distribution of matter on the largest scales. These regions come close to the most gravity-free environments nature allows, though gravity is never truly absent. One of the most beautiful ways we study this faint medium is by observing distant quasars, the brilliant hearts of young galaxies powered by supermassive black holes. As their light travels for billions of years toward us, it passes through thin clouds of intergalactic gas. Specific wavelengths are absorbed, leaving delicate dark lines in the spectrum. By reading these lines, astronomers learn the density, temperature, and composition of the intergalactic medium at different eras, tracing how the universe expanded, how galaxies formed, and how the cosmos was gradually enriched with heavier elements. There is something deeply peaceful in imagining this vast, thin sea of matter. It is not truly empty, yet it is so close to emptiness that the difference almost dissolves. An object could drift here for billions of years without coming near anything substantial. The closest star might be hundreds of thousands of light years away. Gravity is present, but so gentle that motion unfolds at a pace beyond ordinary imagination. If gravity is the force that gathers the universe into stars, planets, and galaxies, then the intergalactic medium is where that gathering has barely begun. Here, atoms and ions float in loose wisps, separated by immense distances, only faintly aware of one another. It is the universe in its most diffuse state, where cosmic expansion has, for now, outpaced gravitational collapse. This quiet realm also hints at the far future. As dark energy continues to stretch space, galaxy clusters will drift farther apart, and the intergalactic medium between them will grow ever thinner. In the distant future, light from one cluster will no longer reach another. Each cluster will become its own island universe, surrounded by an expanding ocean of increasingly rarefied space. The gravitational connection between clusters will fade as they slip beyond one another's horizons, leaving separate cosmic regions isolated by the expansion of space-time itself. Yet that future lies unimaginably far ahead. For now, the intergalactic medium remains a vast and tranquil presence between galaxies, a place where matter exists in its most delicate form, where gravity murmurs instead of commands, where space-time is almost flat and calm. It reminds us that most of the universe is not made of blazing stars or swirling galaxies, but of quiet space, subtle structure, and the gentle backdrop against which the grand story of the cosmos slowly unfolds, inviting the mind to drift, to soften, and to rest in the immense stillness of it all. In the gentle mathematics of gravity, there are special places known as saddle points, quiet locations where gravitational influence becomes momentarily minimal. These are not peaks or valleys in the landscape of gravity, but in between, like a mountain pass where the ground flattens briefly before sloping away in different directions. In these regions, the competing pulls of massive objects can cancel just enough to create a delicate balance, a soft pause in the curvature of space-time. To picture this, imagine gravity as shaping an invisible landscape. Massive objects form deep valleys in this terrain, and lighter regions form higher ground. A saddle point is like a pass between two valleys. If you move along the ridge in one direction, you might not go up or down at first, but step slightly to the side and you begin to descend. In space, this means gravity balances in certain directions, but not in others. It is an equilibrium, but an unstable one, more like balancing a pencil on its tip than resting in a bowl. Consider two stars of equal mass separated by a great distance. Exactly midway between them lies a gravitational saddle point. Each star pulls with equal strength in opposite directions, so along the line between them, the forces cancel. Yet this balance is fragile. A small shift toward either star means its gravity becomes stronger, and the object begins drifting that way, moves sideways, and the geometry changes again, pulling the object back toward the central line. This is the signature of a saddle point, balanced in one direction, unstable in another. Unlike the more familiar Lagrange points that appear in orbiting systems, these simple saddle points arise purely from gravity without needing rotation. In the real universe, everything is moving, orbiting, drifting, so perfectly static saddle points are rare and fleeting. Still, they exist in the mathematics, and they help us understand the subtle structure of gravitational fields. The gravitational potential at any point in space comes from adding together the influence of every mass in the universe. Nearby objects shape the landscape strongly, distant ones more gently. A saddle point appears where all these influences momentarily cancel so that the net gravitational force is zero. But this does not mean the location is safe or stable. The moment something shifts, the balance is lost and motion begins again. In systems with more than two bodies, the pattern becomes even richer. Imagine three stars arranged in a loose triangle. Between each pair there can be saddle points, and there may also be more complex balancing regions where all three influences partially cancel. These locations drift and shift as the stars move, forming a constantly evolving map of gentle balances and instabilities. In binary star systems, saddle point physics appears in a more practical way. When two stars orbit each other closely, there is a point between them where gravitational and rotational effects balance. Gas from one star can flow through this region toward the other, passing through a kind of rotating saddle point. This process shapes the life stories of many binary stars, allowing matter to transfer from one to the other in a slow cosmic exchange. On far larger scales, similar ideas apply between galaxies and even galaxy clusters. If two massive clusters lie tens of millions of light years apart, there must be a place between them where their gravitational pulls balance along the line that connects them. An object placed there would feel very little net pull in that direction, suspended between enormous structures. In reality, the expansion of space and the presence of dark matter make the situation more complex, but the principle remains. Such locations would be among the quietest gravitational environments in the universe. In Einstein's picture of gravity as curved spacetime, a saddle point is a place where this curvature briefly flattens in one direction while remaining curved in another. The geometry becomes subtle and mixed, neither fully curved inward nor outward, but balanced in a delicate configuration. These regions are interesting because they are unstable. A tiny push one way or another determines where an object will ultimately go. In complex gravitational systems, this sensitivity can lead to chaotic motion, where small differences grow over time into very different outcomes. Saddle points act like dividing lines in this cosmic dance, separating paths that lead toward different gravitational homes. For practical space travel, saddle points are not especially useful resting places. A spacecraft positioned at 1 would quickly drift away unless constantly corrected. Even the gentle pressure of sunlight or the smallest gravitational tug from a distant body would be enough to tip the balance. Holding position would require steady adjustments, like trying to remain perfectly balanced on a narrow ridge. Yet there is something quietly beautiful about these places. They show that gravity is not just about falling toward a single object, but about the combined influence of everything in the universe. The result is a vast and intricate landscape filled with valleys, slopes, plateaus, and these fleeting passes where forces momentarily cancel. When we think about saddle points, we are really thinking about balance created by opposition. It is a fragile, temporary stillness, a pause between motions. In these regions, gravity's pull softens almost to nothing for an instant. Space-time briefly smooths, and weightlessness arises not from the absence of gravity, but from its perfect balance. It is another example of how the universe can create calm not only in emptiness, but also in the precise harmony of competing forces, a quiet equilibrium that lasts just long enough to remind us how dynamic and interconnected the cosmos truly is. Galaxies do not end with a sharp boundary. Instead, they slowly fade, their bright central regions giving way to softer and sparser outskirts where stars grow fewer and the pull of gravity becomes gentler. As you move outward through a galaxy, the environment grows quieter. The crowded inner regions thin into a vast halo, a roughly spherical envelope surrounding the galaxy where ancient stars wander, globular clusters travel on long looping paths, and dark matter quietly shapes the motion of everything within it. Out here, gravity still exists, but its grip is softer, and space-time curves with a much lighter touch. Our own Milky Way stretches far beyond the glowing band we see in the night sky. The visible disk of stars extends roughly 50 to 60,000 light-years from the center, but the galactic halo reaches much farther, perhaps 200,000 light-years or more. Beyond even that lies the dark matter halo, an enormous invisible structure that may extend halfway toward the Andromeda Galaxy. In these remote regions, stars are separated by enormous distances. Where our local neighborhood contains stars scattered every few light years, the outer halo may have only one star in a volume so vast it is hard to imagine. An observer living in this distant halo would see a very different sky from the one above Earth. The Milky Way would no longer arch overhead as a bright river of light. Instead, the entire galaxy would appear as a concentrated glow in one part of the sky, like a distant luminous cloud. The rest of the sky would be deep and dark, with only a few nearby halo stars shining faintly and other galaxies standing out more clearly than they do from our position within the disk. Gravity here would feel extremely weak. The combined mass of stars and dark matter in the galaxy still exerts a pull, but at such distances that pull becomes subtle, guiding slow, graceful orbits rather than the faster motions seen closer to the center. Among the most beautiful residents of the halo are globular clusters, dense spheres of ancient stars that travel on long elliptical paths around the galaxy. Each cluster is held together by its own gravity, a tight family of hundreds of thousands of stars moving together through the vast emptiness of the halo. When a globular cluster reaches the farthest point in its orbit, it enters one of the calmest gravitational environments in the galaxy. The Milky Way's pull is present but faint, and the cluster drifts quietly, a glowing island of stars suspended in a sea of darkness. The outer parts of galaxies also hold one of the strongest clues that most of a galaxy's mass is invisible. When astronomers measure how fast stars orbit far from the galactic center, they find those stars move faster than expected. This tells us that an unseen halo of dark matter surrounds the galaxy, adding extra gravity even in these remote regions. Yet, even with this hidden mass, the gravitational field in the outskirts is still far weaker than in the inner galaxy, simply because everything is spread so widely apart. The gentle gravitational conditions of the halo allow fragile structures to survive for billions of years. Streams of stars, the remnants of smaller galaxies torn apart long ago, can still be traced as faint rivers wrapping around the Milky Way. These stellar streams move through the weak gravitational field like slow currents, preserving the memory of ancient mergers that helped build our galaxy. One especially distant companion, known as Leo 1, orbits the Milky Way at an extraordinary distance, hundreds of thousands of light years from the center. Out there, the galaxy's pull is so slight that its orbit takes billions of years to complete. In such places, gravity feels more like a distant suggestion than a strong command, and some objects may eventually drift away entirely, slipping into intergalactic space over immense stretches of time. Defining the true edge of a galaxy is surprisingly difficult because the transition is so gradual. Astronomers sometimes speak of the edge in terms of where stars become extremely rare, or where the dark matter halo thins, or where the galaxy's gravity no longer dominates over the influence of neighboring galaxies and the expansion of the universe. However we define it, the outskirts are a region of transition, where a galaxy's identity slowly blends into the larger cosmic environment. It is even possible that planets exist in these remote regions, orbiting faint halo stars or wandering freely after being ejected long ago. A world out there would have an almost completely dark sky, with only a distant glow marking the home galaxy and the soft light of other galaxies scattered across the void. The planet would feel the gravity of its own star most strongly, while the galaxy's pull would be only a faint background presence. This is life on the edge of a galaxy, where isolation becomes profound and the universe feels vast beyond measure. The outer halos also play an important role when galaxies interact. Long before two galaxies collide directly, their extended halos begin to overlap. Gravity gently stretches them, pulling out long streams of stars and gas that arc through space like luminous ribbons. Objects caught in these tidal streams move in complex gravitational fields shaped by more than one galaxy at once, their futures uncertain as the slow dance of merging continues over hundreds of millions of years. As we travel outward through a galaxy in our imagination, we are really moving along a gradient of gravity, from the strong curvature near the center to the soft, almost flat geometry of the halo. These distant regions are among the quietest places a galaxy has to offer. Gravity is still present, still shaping motion, but it does so with a light touch. The stars move slowly, the distances are immense, and the sense of solitude deepens. Here, at the fading edges of a galaxy, the familiar structure of the cosmos gives way to the vast openness beyond, and the universe feels calm, spacious, and almost perfectly still. Now let your mind drift even farther outward, beyond our galaxy, beyond the scattered glow of other galaxies, past clusters and vast dark regions, traveling always toward the greatest distance we can possibly imagine. Eventually, we reach a profound boundary known as the cosmological horizon, the limit of the observable universe. This is not a wall or an edge in the ordinary sense. It is a boundary set by time and light, a distance so great that light from beyond it has simply not had enough time to reach us since the universe began. Here, the ideas of gravity and space become intertwined with cosmic expansion in ways that feel almost dreamlike. The observable universe is finite, not because the universe must end, but because light has a finite speed and the cosmos has a finite age. When we look far away, we are also looking back in time. The most distant light we can see today has traveled for nearly the entire history of the universe. Because space itself has been expanding during that journey, those distant regions are now far farther away than the light travel time alone would suggest. The observable universe stretches tens of billions of light years in every direction, a vast sphere centered on us, not because we are special, but because this is how far light has been able to travel since the beginning. Near this horizon, space is expanding away from us extremely rapidly. This is not motion through space like a rocket flying away, but the stretching of space itself. Galaxies are carried along as the fabric of the cosmos expands. At a great enough distance, this expansion causes regions of space to recede from us effectively at the speed of light. Light emitted from their struggles to make progress toward us, and in many cases it never will. The horizon is therefore a limit of visibility, a soft boundary between what can in principle affect us and what cannot. In such distant regions, gravity becomes almost irrelevant from our point of view. Gravity is strongest where matter is concentrated, inside galaxies and clusters. But across the immense scales near the cosmological horizon, matter is spread thinly, and the expansion of space dominates the overall behavior of the universe. Any single distant galaxy is so far away that its gravitational pull on us is effectively zero, and our pull on it is just as negligible. The curvature of space-time there reflects the overall geometry of the universe rather than the influence of any one structure. Cosmologists describe this large-scale geometry using elegant mathematical models that treat the universe as smooth and uniform on the biggest scales. In these models, distances between faraway regions change over time according to a cosmic scale factor, a gentle stretching that has been underway for billions of years. Near the horizon, this stretching becomes the dominant story. Gravity still exists, but it no longer gathers matter into new structures across those distances. Instead, expansion carries regions ever farther apart, slowly reducing their ability to influence one another at all. There is also a future boundary to consider. Because the expansion of the universe is accelerating, driven by dark energy, there are galaxies whose light will never reach us no matter how long we wait. Over immense spans of time, more and more of the universe will slip beyond this future horizon. Distant galaxies will fade from view, their light stretched and dimmed until they disappear entirely. From our perspective, they will become gravitationally and causally disconnected, part of a cosmos we can never again observe or interact with. The faint glow of the cosmic microwave background offers us a glimpse of conditions close to our observable limit. This ancient light began its journey when the universe was very young, long before stars and galaxies formed. It comes to us from a spherical shell surrounding us at an enormous distance, marking the farthest region we can see using light. Beyond that lies an earlier, opaque universe, and then regions we cannot observe directly at all. Yet we know the cosmos continues beyond, vast, and largely unreachable. On these scales, gravity is no longer about falling apples or orbiting planets. It becomes part of the overall shape and fate of the universe. Observations suggest that space on the largest scales is very close to flat, meaning that over immense distances the geometry of the cosmos follows the familiar rules of straight lines and gentle angles. This near flatness is one of the great clues to the universe's early history and hints at a brief period of extremely rapid expansion long ago that smoothed out any strong initial curvature. There is something deeply calming about contemplating the cosmological horizon. It represents the ultimate distance, the farthest reach of our possible awareness. Beyond it, events cannot influence us, and we cannot influence them. In that sense, gravity across such distances has faded into insignificance, not because it has been canceled or shielded, but because the expansion of space has carried regions so far apart that interaction itself becomes meaningless. These are the quietest realms of all, where the universe stretches beyond sight, where light thins and reddens, where the connections between distant places grow ever weaker. Thinking about these far horizons can feel like floating at the edge of everything we can know, surrounded by an immense, gentle vastness. Gravity still shapes stars and galaxies closer to home, but out here its voice is almost silent, replaced by the slow, steady breathing of cosmic expansion. In this immense stillness, the universe feels open, spacious, and calm, inviting the mind to rest in the idea of endless distance and the soft fading of all forces into the background of an ever-widening cosmos. Physics allows for the possibility of many phenomena that have never been directly observed, yet still remain consistent with our mathematical understanding of the universe. These hypothetical structures, predicted by general relativity or by more speculative extensions of modern physics, invite us to imagine some of the most unusual gravitational environments possible. In these places, gravity might behave in unfamiliar ways, or in certain regions, seem to almost fade from influence altogether. Although these ideas remain theoretical, exploring them gently expands our sense of what space, time, and gravity might truly allow. One of the most well-known examples is the concept of a white hole. A white hole can be imagined as the time-reversed counterpart of a black hole. While a black hole is a region of space-time from which nothing can escape, a white hole would be a region that nothing could enter. Matter and energy would only move outward, never inward. Its boundary, similar in concept to an event horizon, would act as a one-way surface, but in reverse. Instead of trapping everything inside, it would prevent anything from crossing into it. The gravitational environment near a white hole would be deeply strange. Around a black hole, gravity grows stronger as matter falls inward. Near a white hole, matter would appear to move outward against an inward pull of gravity, creating a situation that feels almost paradoxical. Just outside the boundary, gravity would still curve space-time inward toward the mass, yet nothing could actually fall in. The surface itself would highlight the difference between gravity as a force we feel and gravity as the geometry of space-time itself. Most physicists suspect that white holes do not truly exist in our universe. They appear to be unstable solutions within Einstein's equations, and even if one could somehow form, it might collapse into a black hole almost instantly. Their formation would also require extremely special conditions, almost like running the history of a black hole backward in time. Even so, they remain mathematically valid, and simply thinking about them helps us better understand the full range of what general relativity describes. Another fascinating possibility is the cosmic string. These would be incredibly thin defects in space-time that may have formed during phase transitions in the very early universe. A cosmic string could be thinner than a proton, yet stretch across distances larger than entire galaxies. Despite their thinness, they could contain enormous mass per unit length. The gravitational effect of a cosmic string would be very different from that of a star or planet. Instead of pulling objects inward in the usual way, the space around a string would take on a conical shape, as if a tiny slice of space had been removed. In such a geometry, light and matter passing near a cosmic string would change direction, not because they were pulled toward it, but because the shape of space itself is altered. In some simplified models, an observer moving near a cosmic string might feel almost no direct gravitational pull at all, even though the path of motion through space is subtly bent. It would be a place where gravity is present in geometry, but quiet in sensation. Domain walls are another speculative idea. These would be two-dimensional surfaces separating regions of space where the vacuum exists in different states. Like cosmic strings, They could have formed during symmetry-breaking events in the early universe. A domain wall would carry enormous energy spread across its surface. The gravity associated with such a structure would not behave like the gravity of a planet or star. In simple descriptions, matter on both sides would be drawn toward the wall, but the gravitational influence could become negligible at great distances. Far away, space might feel almost normal, while closer regions would experience a gentle but persistent attraction toward the surface. Some cosmological models go even further, suggesting that our entire observable universe might be just one bubble within a much larger multiverse. In these ideas, space beyond our bubble could follow different physical rules. The boundaries between such bubbles, or the vast regions between them, might host gravitational conditions very different from those we know. In some areas, gravity might be extremely weak or behave according to unfamiliar laws. These concepts remain highly speculative, but they help physicists explore gravity in its most general and flexible form. Gravastars offer yet another imaginative alternative to black holes. In this model, what appears to be a black hole from a distance is actually a thin shell of exotic matter surrounding a region filled with vacuum energy. Unlike a black hole, a gravastar would have no singularity at its center. Inside the shell, the negative pressure of vacuum energy could counterbalance gravity so effectively that the interior space-time becomes nearly flat. This would create a hidden region where gravity is astonishingly weak, enclosed within an object of immense mass. While observations currently support the existence of traditional black holes, the gravastar idea shows how many different gravitational structures are allowed by theory. Wormholes, often called bridges through space-time, are another feature permitted by general relativity. A wormhole would connect distant regions of the universe through a tunnel-like geometry. At the narrowest part, known as the throat, gravity could behave in unusual ways. Depending on the structure, gravitational pulls from different directions might balance each other, creating directions in which an object would feel almost weightless. However, keeping such a passage open would require forms of matter with negative energy density, something that remains deeply uncertain in practical terms. A related idea is the Alcubierre drive, a speculative concept for faster-than-light travel. This proposal suggests that a spacecraft could sit inside a bubble of nearly flat space-time, while space in front contracts and space behind expands. Inside this bubble, passengers would not feel extreme gravitational forces. The strange curvature would be confined to the boundary of the bubble, leaving the interior calm and nearly gravity-free. Like wormholes, this concept depends on exotic forms of energy that we do not yet know how to produce in useful amounts, but it remains an intriguing solution within Einstein's equations. At even smaller scales, some theories of quantum gravity suggest that space-time itself may have a restless, foam-like structure. At distances near the Planck length, space and time may fluctuate constantly, with tiny wormholes and curved regions appearing and disappearing in brief quantum events. In such a realm, the idea of a stable gravitational field becomes less clear. Geometry itself would shimmer with uncertainty, though far beyond anything we can observe directly. This picture represents the frontier where gravity and quantum physics begin to merge. All of these possibilities remind us that our understanding of gravity, as powerful as it is, remains incomplete. General relativity works beautifully on large scales, but it does not yet fully unite with quantum mechanics. A deeper theory of quantum gravity may one day reveal entirely new structures and environments, including places where gravity behaves in ways we have not yet imagined, or where its influence becomes almost absent. The speculative nature of these ideas does not lessen their value. Instead, they gently stretch our imagination and deepen our sense of wonder. They suggest that the universe may be far richer and more varied than our current observations reveal. Somewhere, beyond the limits of what we can yet measure, there may be regions where gravity is subtle, unusual, or nearly silent, waiting quietly at the edge of understanding. And as we continue this journey, we return from these distant theoretical possibilities to the gravitational environments that may exist within our own cosmic landscape, places where gravity is not entirely gone, but where it grows weaker in ways that shape the motion of worlds and the structure of space itself. Not all places where gravity feels faint are hidden in the far reaches of the cosmos. Some are much closer, found in environments shaped either by nature or by human ingenuity, where the pull of gravity is softened and the body drifts in a state we call microgravity or near-weightlessness. These places have become quiet laboratories for discovery, teaching us how deeply gravity influences everything from the way flames burn to how our own bodies function. They remind us that weightlessness is not only about being far from massive worlds, but also about motion, balance, and the subtle dance between falling and moving forward. One of the most familiar microgravity environments exists aboard the International Space Station, circling Earth at an altitude of about 400 kilometers. It may seem surprising, but gravity there is still strong, roughly 90% of what we feel at Earth's surface. Astronauts float not because gravity has disappeared, but because they, the station, and everything inside it are in continuous free fall together. They are constantly falling toward Earth, yet moving forward so quickly that the planet curves away beneath them. In this shared fall, there are no supporting forces pushing up from the floor, and so the body experiences the gentle, drifting sensation we call weightlessness. This distinction is important and often misunderstood. Microgravity does not mean gravity is gone. It means its effects are not felt in the usual way because all nearby objects accelerate together under its influence. Once in orbit, this state requires no continuous thrust. The station loops around Earth roughly every 90 minutes, traveling at about 7.6 kilometers per second, a graceful balance between forward motion and gravitational pull that keeps it circling at a nearly constant height. Even so, the microgravity aboard the station is not perfectly uniform. Tiny variations in Earth's pull create what are known as tidal forces. Parts of the station slightly closer to Earth feel a bit more gravity than parts farther away, producing extremely small stretching effects along the Earth-facing direction. These forces are minuscule, around a millionth of surface gravity, yet sensitive instruments can detect them. There is also a whisper of atmospheric drag at that altitude, enough to slowly reduce the station's speed. Periodic boosts from visiting spacecraft restore its orbit, and during those gentle engine firings, the crew briefly feels small accelerations before returning to their drifting routine. Another path to microgravity comes through parabolic flight. Special aircraft climb steeply and then arc downward along a trajectory that mirrors the path of a freely falling object. During the top of each arc, everyone inside the plane is in free fall together, experiencing about 25 to 30 seconds of weightlessness. These flights have trained astronauts and allowed researchers to perform short experiments in microgravity. The sensation is similar to that in orbit, though it arrives in brief, repeating waves, separated by periods of normal gravity as the aircraft prepares for the next arc. Microgravity also appears naturally in deep space. A spacecraft coasting between planets with its engines off follows a path shaped by the gentle pulls of the sun and distant worlds. Everything inside shares that motion, creating a continuous state of free fall. As the craft travels farther from major masses, the gravitational accelerations grow weaker still, approaching the extremely low gravity conditions found in the vast spaces between stars. small asteroids and tiny moons offer another kind of low-gravity environment, different from true microgravity, but still remarkably gentle. On the surface of a small asteroid, there is a real downward pull toward its center, yet it can be thousands of times weaker than Earth's gravity. On an object like the asteroid Eros, a person who weighs 100 kilograms on Earth would weigh only a few tens of grams. A simple push could send you drifting upward in a slow arc, and a strong jump might be enough to leave the surface entirely. Movement there would be cautious and deliberate, with every step needing care to avoid floating away. The smallest asteroids, only a few meters across, blur the line between solid ground and open space. Their gravity is so faint that loose material barely clings to the surface. A gentle disturbance could send dust or pebbles drifting off into the darkness. These tiny bodies mark a transition between worlds where gravity still shapes the surface and regions where motion is almost entirely free. Research in microgravity has revealed behaviors rarely seen on Earth. Flames become round and soft, forming glowing spheres because hot gases no longer rise. Liquids gather into shimmering globes, guided mainly by surface tension, clinging to containers in ways that look almost alive. Without gravity-driven buoyancy, convection currents fade, and heat and particles spread more slowly and evenly. Crystals can grow with fewer imperfections, undisturbed by the settling of heavier components. These subtle differences have deepened our understanding of physics, materials, and biological processes. The human body, too, responds strongly to life without weight. Bones begin to lose density, no longer stressed by supporting the body's mass. Muscles weaken when they are not used to stand and move against gravity. The heart and blood vessels adapt to a world where fluids no longer pool in the lower body. Astronauts exercise for hours each day to counter these changes, yet some effects still appear over long missions. The inner ear, which normally senses up and down through gravity, becomes confused at first, often causing space motion sickness. These responses reveal how completely our biology has grown around the steady pull of Earth. To make long-term living in space more comfortable, future habitats may spin to create artificial gravity. In a rotating structure, the outward push felt in the rotating frame can press people gently against the outer wall, which becomes the floor. Though this is not gravity produced by mass, it mimics many of its practical effects. Objects fall toward the floor, liquids settle, and the body experiences a steady load. Some unusual sensations would remain, such as slight sideways forces on moving objects, but thoughtful design could make these environments feel natural and stable. Whether created through orbit, aircraft maneuvers, deep space travel, or the weak pull of small worlds, microgravity environments offer a rare chance to observe nature with gravity's influence turned down. They also give us a preview of life in regions of the universe where gravity is truly faint, the kinds of places we have imagined among cosmic voids and distant expanses. The drifting experience of astronauts aboard the space station is a small echo of what it might be like to float between galaxies, unanchored, moving in quiet harmony with the curvature of space. There is a calmness to these environments, a freedom from the constant downward pull that shapes nearly every moment on Earth. Up and down lose their usual meaning, and movement becomes three-dimensional and fluid. Those who have lived in microgravity often speak of wonder, of seeing familiar laws revealed as local conditions rather than universal rules. By studying and experiencing microgravity, we take another step toward understanding the wider cosmos, where gravity's strength changes from place to place, creating an endless variety of gentle, powerful, and nearly weightless realms spread across the universe. If we let our thoughts drift forward through unimaginable stretches of time, beyond the lifetimes of stars and the slow reshaping of galaxies, we arrive at a future universe that feels almost unrecognizable. This is the domain of cosmological eschatology, the study of the universe's long-term fate, where gravity gradually loses its role as a grand organizer and the cosmos moves toward maximum entropy and minimal structure. In this distant era, trillions upon trillions of years from now, most of existence will unfold in places where gravity barely plays a role, not only because matter is spread far apart, but because the universe itself will have evolved into a state where meaningful gravitational interactions become rare and eventually almost irrelevant. Observations today show that cosmic expansion is accelerating, driven by dark energy, a mysterious component that makes up most of the universe's total energy content. Dark energy behaves much like a cosmological constant, creating a gentle negative pressure that causes space itself to expand faster and faster over time. As this expansion continues, galaxy clusters that are not tightly bound by gravity drift farther apart, carried away by the stretching of space. In a few trillion years, galaxies beyond our local group will have receded so far that they will no longer be visible from the Milky Way or any world within it. Their light will be stretched to wavelengths so long that it fades beyond detection, and they will pass beyond our cosmic event horizon, a boundary beyond which signals can never reach us. The observable universe will slowly contract to include only the structures gravitationally tied to us, mainly the Milky Way, Andromeda, and their smaller companions, which will eventually merge into a single large galaxy, often nicknamed Milkomeda. Within this merged galaxy, star formation will continue for a time, but the raw material for new stars is limited. Gas will be used up, locked into stars, or blown away by stellar winds and explosions. Massive stars will have long since ended their lives, leaving behind neutron stars and black holes. Sun-like stars will swell into red giants and settle into white dwarfs, hot at first but gradually cooling. The smallest stars, red dwarfs, will shine the longest, for trillions of years, yet even they will one day exhaust their fuel. After roughly 100 trillion years, the era of active star formation will be over. What remains will be a quiet collection of stellar remnants, white dwarfs, neutron stars, black holes, brown dwarfs, and cold planetary bodies. The galaxy will be dim, lit only by the fading warmth of cooling remnants and the occasional burst of radiation as matter falls into black holes. Gravity will still bind these objects together, guiding their slow orbits around the central mass, but the lively gravitational encounters of younger galaxies will have largely faded. Over far longer times, gravity itself will slowly reshape what remains. Close passes between stellar remnants will sometimes fling objects out of the galaxy entirely, a process known as evaporation. Others will gradually spiral inward through subtle gravitational interactions, eventually being swallowed by the central black hole. After spans of time on the order of 10 to the 19th or 20th years, most objects will have either been ejected into deep space or absorbed, leaving little more than a supermassive black hole and a thin sprinkling of distant escapees. The galaxy's once rich structure will have mostly dissolved. Those ejected remnants will drift into a vast and lonely darkness. By then, cosmic expansion will have carried all other galaxies far beyond any possible contact. These wandering objects will move through an ever-growing void, feeling gravitational pulls so faint they are practically indistinguishable from nothing at all. There will be no nearby stars to orbit, no clusters to belong to, only slow motion through emptiness under the almost silent influence of distant, unseen masses. Even black holes, which seem eternal, are not forever. Quantum effects near their boundaries cause them to emit an extremely faint glow known as Hawking radiation. This process makes black holes lose mass at an almost unimaginable slowness. A black hole with the mass of our Sun would take around 10 to the 67th years to fully evaporate, while supermassive black holes could last about 10 to the 100th years. These numbers are beyond ordinary comprehension, yet they are still finite. After black holes fade, the universe may grow quieter still. Some theories suggest that protons, the building blocks of atomic nuclei, might eventually decay, though this has never been observed. If they do, then over immense timescales, all familiar matter would dissolve into lighter particles and radiation. White dwarfs, neutron stars, planets, and every solid structure would slowly disintegrate, leaving a cosmos filled mostly with faint radiation and a thin sea of elementary particles spread across an ever-expanding space. In such an era, gravity would lose any significant role in shaping the universe. There would be no stars, no galaxies, no dense structures to curve space in noticeable ways. The universe would approach what is called heat death, a state of maximum entropy where energy is evenly spread and no usable gradients remain to power change. In that calm equilibrium, the idea of gravitational field strength becomes almost meaningless because there are no major concentrations of mass anywhere. Space would be nearly flat and extraordinarily empty, with particles separated by distances so vast that each might as well inhabit its own private cosmos. Some scientists explore even more speculative futures. If dark energy were to grow stronger over time, expansion could accelerate so dramatically that it would eventually tear apart galaxies, stars, planets, and even atoms in a scenario known as the Big Rip. In that case, gravity would be overwhelmed completely by cosmic expansion. Current evidence, however, points more toward a steady dark energy that leads to gradual cooling and dilution rather than violent destruction. Another possibility comes from quantum theory. The vacuum of space might not be in its lowest energy state. If a more stable state exists, a bubble of this true vacuum could form and expand at light speed, transforming the laws of physics as it goes. Such a transition could alter the strengths of fundamental forces, including gravity, though the details are deeply uncertain and remain in the realm of theory. While these distant futures can sound bleak, they can also be viewed as a kind of cosmic stillness. The intense drama of the early universe, its blazing radiation and crowded structures, will have long since given way to a cool, dark, and quiet expanse where change unfolds at a pace so slow it is almost imperceptible. Gravity, once the great architect of stars and galaxies, will whisper only faintly across enormous emptiness. Thinking about this far future places our own moment in perspective. We live in a rare and lively era when stars shine brightly, galaxies interact, and gravity actively sculpts the cosmos on every scale. This vibrant chapter is brief compared with the immense stretches of time to come. Most of the universe's history still lies ahead in a far calmer and darker state. In that sense, we exist during a youthful and dynamic phase, before gravity's shaping influence fades and the cosmos settles into its final, quiet equilibrium. The deep future universe will be a place where gravity barely exists, not because of unusual locations or exotic objects, but because matter will be so widely dispersed and structures so thoroughly dissolved that gravitational effects become vanishingly small everywhere. It will be the ultimate low-gravity environment, a vast, expanding expanse where the force that once governed orbits, built galaxies, and lit the stars has thinned to a faint trace, leaving behind only the subtlest curvature of space across an almost empty cosmic ocean. Throughout our journey exploring places where gravity barely exists, we have mostly looked at the physics and astronomy of these regions. Now we can gently turn toward a more personal question. What would it actually feel like to exist in such places, to live and experience awareness where gravity has only a faint presence? This brings us into the realms of biology, psychology, and philosophy, and invites us to reflect on how deeply gravity shapes not only the universe around us, but also the living beings within it and their sense of being. Life on Earth evolved under the steady pull of gravity, and every layer of biology carries that history. The forms of plants and animals reflect constant adaptation to weight and support. Trees grow strong trunks to hold themselves upright. Animals rely on bones and muscles to carry their bodies against the downward pull. The heart works continuously to move blood upward. Even within cells, tiny structures and fluids behave in ways subtly influenced by gravity. When that pull is reduced or removed, many of these long-established patterns begin to change. Experiments in space have shown that living systems respond in surprising ways to low gravity. Some bacteria grow in thicker, more protective layers. Plants grow in unusual directions when they no longer sense a clear up or down. On Earth, roots grow downward because specialized cells respond to gravity. But in orbit, those signals become unclear and other cues take over. Growth becomes a quieter negotiation with light, moisture, and touch rather than a firm response to weight. The human body also changes in gentle but significant ways. Bones become less dense when they are no longer loaded by body weight. Muscles, especially those that keep us upright, gradually weaken. The heart and blood vessels adapt to a world where fluids no longer pool in the lower body. People returning from long stays in space often need time to readjust, as their bodies remember what it means to live under a stronger gravitational pull. These changes remind us that gravity is woven deeply into our biology, shaping us from the inside out. If humans one day live for long periods in low gravity, on the Moon, on Mars, or in free-floating habitats, we will need new ways to stay healthy. Rotating habitats could create artificial gravity through steady spinning, giving the body familiar signals again. Other solutions might come from medicine or technology that helps bones and muscles stay strong. All of these ideas are still developing, but they show how closely our well-being is tied to the quiet force that holds us to the ground. Beyond biology, low gravity would gently reshape daily experience. On Earth, we always know where down is. Our sense of direction is constant and automatic. In weightlessness, that certainty fades. Up and down lose their meaning, and every direction becomes equally natural. People who have lived in orbit often describe this as freeing, as if space itself becomes a place you can move through like water, slowly and effortlessly. Over time, the mind adapts, and a new sense of orientation forms, one based more on vision and intention than on gravity. There would also be emotional and psychological effects. Living far from Earth in a place where gravity barely holds you would bring a strong sense of distance and isolation, but also a feeling of openness and perspective. Seeing Earth as a small, bright world in the distance can deepen the sense that all life shares one fragile home. Many astronauts speak of a quiet shift in awareness, a feeling of connection and calm that comes from floating above the boundaries that usually divide us. Gravity gives us grounding in a very literal sense, and also in a symbolic one. It anchors us, gives weight to our steps, and a stable frame for our movements. Without it, we might at first feel unmoored, but we might also discover a different kind of balance, one that comes from within rather than from the pull of a planet. In this way, low-gravity environments are not only physical frontiers, but inner ones, inviting new ways of sensing space, self, and connection. If life exists elsewhere in the universe, It may have grown under very different gravitational conditions. On worlds with weaker gravity, living beings might grow taller and more delicate. On heavier worlds, they might be compact and strong. Any civilization that ventures into space would face the same gentle challenge we do, learning how to live and thrive where gravity is no longer a constant companion. There is a quiet beauty in imagining life in places where gravity barely exists. These regions are the outskirts of cosmic structure, far from dense centers of mass. To live there would be to live at the edge, in wide, open stillness. Such places might feel lonely, but also peaceful, free from many of the forces that shape crowded cosmic neighborhoods. For now, our experiences of low gravity are brief and rare, but they offer a small preview of what is possible. As we look toward future journeys and settlements beyond Earth, we are invited to think not only about rockets and habitats, but about how living minds and bodies will feel in those gentle environments. In doing so, we come to see gravity not just as a force in equations, but as a quiet partner in our existence, shaping how we move, grow, and understand our place in the vast and mostly weightless universe. We have traveled gently through the regions of the universe where gravity barely makes itself known. From the delicate balance of Lagrange points to the immense openness of cosmic voids, from the quiet stretches between galaxies to the more theoretical realms of exotic structures and the distant future of a cooling cosmos, we have been exploring the softest corners of reality, places where gravity fades into the background and space feels almost undisturbed. What connects all of these environments is a sense of absence or balance. Sometimes gravity is weak because there is very little matter nearby, like in cosmic voids or the deep spaces between galaxies where matter is scattered so thinly that space-time is only gently curved. In other situations, gravity is not missing but perfectly balanced, as at Lagrange points where the poles of different bodies cancel each other with quiet precision. And in orbit, objects fall together in such a way that weight seems to disappear, creating the experience of microgravity even though gravity is still present. Each of these situations creates a kind of stillness. It is a pause in the usual gravitational motion that shapes stars, planets, and galaxies. These are places where matter is not being strongly pulled in one direction, where the usual dance of orbits and attraction softens, and where equilibrium can exist for long stretches of time. In a universe often defined by motion and structure, these regions feel like moments of rest. There is something naturally calming about imagining such places, even though they are often cold and dark. They represent the universe in a quieter state, like a long breath held between movements. While galaxies turn and stars travel their paths, these low-gravity regions remind us that the cosmos also contains stillness, wide open expanses where very little happens and space simply extends in silence. As we have explored these ideas, we have also deepened our understanding of gravity itself. We can think of it as a pull between masses, but also as the gentle shaping of space-time. It organizes the universe on every scale, guiding planets in their orbits and helping form the vast web of galaxies. Yet its influence is not the same everywhere. In some regions it dominates completely, while in others it becomes so faint that it is almost impossible to notice. Seeing both sides of gravity, its strength and its softness, gives us a more complete picture of the universe. Reality is shaped not only by attraction and structure, but also by openness and balance. The spaces between things are just as important as the things themselves. The quiet regions help define the brighter, denser ones, creating contrast in the grand design of the cosmos. As we come toward the end of this journey, it helps to reflect on why these nearly weightless places capture the imagination. Perhaps they suggest a kind of freedom, a release from the constant pull we feel every moment of our lives. Or perhaps it is simply their vastness and unfamiliarity that fills us with wonder. These regions feel distant from everyday experience, and that distance invites curiosity and awe. There is also a simple beauty in the idea of gravitational quiet. These places are like the calmest landscapes of the universe, wide clearings in the cosmic wilderness. They are spaces where motion slows, where the usual forces ease their grip, and where existence feels lighter and less constrained. In dreams, we sometimes float or fly, and these regions are where such feelings truly belong in the physical universe. As you relax and let these thoughts settle, you can picture them one more time. Imagine the invisible balance points in space where forces meet in harmony. Picture the vast cosmic voids stretching across unimaginable distances, where galaxies are few and gravity is only a faint presence. Since the thin intergalactic medium, atoms spread so far apart that space feels almost empty. Think of the far future, when the universe will be cooler, darker, and more peaceful, with gravity shaping less and less of what remains. Let these images bring a sense of calm. They remind us how large and varied the universe is, and how many different conditions can exist beyond our everyday surroundings. They also offer perspective. You are part of a world held together by gravity, orbiting a star, within a galaxy shaped by this same quiet force. And yet, even in such a universe, there are places where gravity loosens its hold, where space opens and balance replaces pull. Rest your thoughts in those gentle regions. Imagine drifting through wide, silent expanses where nothing presses down and everything moves slowly and freely. Let the stillness of cosmic voids soften your mind. Let the quiet balance of gravitational equilibrium bring a sense of order and ease. In these images, the universe is simple, spacious, and calm. The cosmos is filled with extremes, with powerful forces and dramatic events, but also with these peaceful zones of near weightlessness. As you drift toward sleep, carry the feeling of those quiet places with you. Somewhere out there, beyond stars and galaxies, gravity grows faint and space stretches in serene silence, holding the universe in a gentle, endless calm. And as your breathing slows, you can imagine that you too are part of that calm expansion, your thoughts widening like the space between galaxies, your worries drifting farther apart until they no longer pull on you with the same weight. In this mental quiet, there is nothing you need to solve, nowhere you need to go, only the steady sense of floating in a vast and patient universe where everything unfolds at its own unhurried pace. In these imagined regions of near weightlessness, time itself seems to soften. Without strong forces shaping every motion, change happens gently, almost imperceptibly. You can picture distant particles drifting for millions of years without meeting anything at all, tracing slow paths through space that feels more like an open ocean than a crowded landscape. This slowness can be comforting. It reminds us that not everything in the universe is urgent or intense. There are places where existence is quiet and steady, where events unfold so gradually that they resemble stillness. As you continue to relax, you might imagine yourself observing such a region from a place of safety, simply watching faint points of light scattered across immense darkness. There is no need to measure distances or understand every detail. The scale itself becomes part of the calm. When space is that wide, when gravity is that gentle, nothing rushes. Even light takes ages to cross the emptiness. Moving patiently through the dark, let your mind mirror that patience. Thoughts can drift in and out without needing to be held onto. Just as matter in a cosmic void is free from strong pulls, your attention can float without pressure. If a thought appears, you can notice it and let it continue on its way, like a lone particle crossing intergalactic space. There is room for everything, and no need for anything to stay. In this way, the universe becomes a quiet guide for rest. Its most silent regions show us a different rhythm, one not driven by urgency, but by gentle continuity. Even gravity, the force that builds stars and galaxies, has places where it steps back and allows stillness to take over. Imagining those places can help the body loosen and the mind settle, as if you too are entering an environment where the usual pressures have eased. Your muscles can soften, your breathing can find an easy pattern, and your awareness can widen, becoming less focused on any single concern and more attuned to a general sense of spacious calm. As this journey comes to its quiet close, you can let the images grow softer and more distant, like stars fading into the background of a brightening dawn. The idea of places where gravity barely exists becomes less a scientific concept and more a feeling, a sense of openness and lightness that you carry within. The universe, in all its vast complexity, also contains these simple regions of balance and calm, and by imagining them, you give your mind permission to rest in a similar way. There is a gentle reassurance in knowing that not all of existence is shaped by intense forces or dramatic events. Much of the cosmos is quiet, spacious, and slow. In that quiet, there is stability of a different kind, not the stability of being held tightly in place, but the stability of having nothing that needs to be resisted. You can allow yourself to settle into that kind of ease now. Feel the surface beneath you supporting your body, just as gravity supports the worlds and stars we have spoken of, and at the same time imagine your thoughts becoming lighter, less tied down, more like the faint structures in distant space. You are both grounded and free, held and open. The universe makes room for both experiences, and so can you. As sleep approaches, there is no need to hold on to the details of this journey. The images of voids, distant futures, and delicate balances can blur into a general sense of peace. Let that peace be enough. Let it carry you gently, like a slow drift through a region where gravity has grown quiet, and space itself feels like a calm, endless sea. In that stillness, you can rest, knowing that just as the cosmos contains places of profound quiet, your own mind can return to quiet too, again and again, whenever you allow yourself to float into rest.